Yeah. In today's lecture we are going to cover one of the very important approaches to material synthesis, because this is both having the capability of making high temperature materials in a non-conventional way, but yet it involves a typical wet chemistry route. As you have seen in the previous lecture, there are a portfolio of chemical synthesis available for making wide range of molecules, and in today's lecture I am going to single out one of the potential preparative route which has been exploited by many groups, and still this particular approach has not been aborted by the researchers, because there is lot more novel insights coming out of this particular process called combustion synthesis. And this combustion synthesis is specially earmarked for high temperature materials, because the energetics that is involved in this combustion route is actually coming from a chemical synthesis which achieves very high temperature, and therefore it is possible for us to realize materials which are otherwise prepared only at very high temperatures. Now when I talk about high temperature materials, these are not the usual chemical compounds that we prepare in lab scale with simple hydrolysis or refluxing, because this is the typical chemistry routes which is commonly seen in any wet chemistry lab. But what we are seeing here is we are starting with the wet chemical approach, but we are realizing very high temperatures, as you would see from this cartoon. So I will just take you through this course of combustion synthesis and tell you what is the principle behind this approach, and what are the advantages, and what is the chemistry that we learn from this, and where do we go from here. As you know, when you talk about high temperature and when you talk about combustion, the first thing that comes to your mind is about launching of satellites or spacecrafts. Now what you see here is a launching pad, and lot of energy is released to take this space shuttle out of the earth orbit, and this is again what you see in this right side is a Japanese space shuttle which is ready for launching. But the essence of this whole payload to go out of Earth's orbit is dependent on whether it is a solid rocket or a liquid rocket, meaning a solid rocket consists of a solid fuel as the combustion material, and as a result it can carry the whole space shuttle and put it in the outer orbit. Now what is important in this solid rocket is the solid propellants, and solid propellants are nothing but a mixture of fuel and oxidizer, and this is the essence of any space applications. Now the beauty of it is, if we understand the principle that governs this launching, then we will know how we can translate that for material synthesis. So in the first few slides I will take you through the essence of what a propellant is, what it means to have a fuel and a oxidizer, and how we can convert this enormous energy into a controlled energy for making materials. Now before I go into the details, I just single out some of the issues related to propulsion. Propulsion can be either solid propulsion or liquid propulsion, and many countries have been using this systematically to put their space shuttle in the outer orbit. Now if you look at India, for example, India has attempted many space launches, of which they have used 19 with solid propellants and 15 with liquid propellants, and out of 19 they have only failed once, and with liquid propellant it is zero failure, and they have done it quite systematically with both solid and liquid propellants. If you look at USA and USSR, you can see USSR has heavily relied on liquid propulsion for their space launches, whereas US has been using both the techniques very judiciously. Japan, for example, if you see, they have relied more on solid propellants than the liquid propellants. Now, what is the advantage and why these propellants can become divisive in the space launches? You can see that the energy that this propellants carry is very vital, and as a course of time, the time evolution of energy is plotted here as early as minus 500 AD or 3500 BC. People were using bow and arrow. Now, if you keep on looking how the energy situation has surfaced, you can see that from there we have graduated to black powder, then to ammonium nitrate, then potassium perchlorate, and silver fulminate, nitro starch, so on, and somewhere here in this arena where we are now living, we have now transposed mostly to RDX, which is nothing but a composite. RDX, Cl20, high N, all these are basically a polymer composite based propellants which are being used. Now, these are hybrid varieties of propellants that are used in space launches. Now, these are also used for several defense purposes. Now, to take a simple definition of a propellant, it is a chemical mixture that is burned in the presence of air to produce thrust in rockets, and it consists of a fuel and a oxidizer. A fuel is a substance which burns when combined with oxygen, producing gas for propulsion. So, when you need oxygen to burn a fuel, then you resort for a material which can give oxygen within rather than take oxygen from outside. That is why the concept of a oxidizer comes. The oxidizer is one which releases enough oxygen for the fuel to burn. So, if you have a proper chemistry between this fuel and oxidizer, then you can release enormous energy, therefore you can get the thrust that you want. So, an oxidizer is an agent that releases oxygen for combination with the fuel. The ratio of oxidizer to fuel is called the mixture ratio, and in propellant chemistry it is usually called as mixture ratio. Now, we use this word more frequently and call this oxidizer to fuel ratio or O/F ratio. Propellants actually are classified in different ways. They need not be solid always. We can look at some of the definitions. For example, liquid propellants used in rocket applications can be classified into three: petroleum, cryogens, and hypergols. What is important is this hypergolic propellants, because they are fuels and oxidizers that ignite spontaneously on contact with each other. When you just bring both the oxidizer and fuel in physical contact, immediately they become hypergolic and they get ignited. That is the definition of a hypergolic propellant. They are easy and the starting capability of the hypergols make them really ideal for spacecraft maneuvering. Therefore, hypergolic propellants are much more used nowadays than even petroleum and other cryogens. Now, what are these hypergolic fuels? Hypergolic fuels are commonly known as hydrazine or monomethyl hydrazine, popularly abbreviated as MMH in rocket technology, and hydrazine gives the best performance as a rocket fuel. As you know, hydrazine is nothing but N2H4, and this N2H4 can be substituted with methyl groups. So, they are called as unsymmetrical dimethyl hydrazine, where two methyls can be substituted here and two hydrogens can be here, or it can be a monomethyl. Both are found to be extremely useful hypergolic fuels. The oxidizer in this case is actually nitrogen tetroxide or nitric acid. So, just bring hydrazine and in contact with nitrogen tetroxide, immediately they burn to give the necessary heat. Now, how do propulsion occurs, or how can we propel this combustion principle to make material synthesis is our question, because the energy that is released is uncontrollable. You just can't fashion it, you can just put a big mass into the space. So, this has to be retained or confined into a lab situation is a big challenge. Therefore, how do we propel this combustion for material synthesis is a $1,000,000 question, and we will look at it. It is not new per se, because the principle of combustion for high temperature synthesis has been there for many years, and the most important one is the thermite reaction, which is nothing but burning aluminum with iron oxide, and if you burn, it converts into aluminum oxide and iron. This is called a thermite process, which is usually used in joining or welding railway tracks, and this was pioneered by Goldsmith in 1898 to prepare metals and alloys. Therefore, this is not a new phenomena to make materials, but this is often categorized as self propagating high temperature synthesis, because this has been used to achieve very high energy to prepare new materials. Walton and Paulus have prepared refractory ceramides, which are usually alumina based or zirconia based ones, which are doped with some 3D transition metals. But the concept of self propagating high temperature synthesis was actually exploited more by Mersanova. So, I would like to show his portrait, because he was one of the pioneers in this field who brought in a lot of fundamental applications of this SHH technology for applications. Mersanova have used a metal fuel and a non-metal oxidizer to prepare borates, carbides, silicides, cermet hydrides and nitrates. If you want to prepare nitrates, then you need to mix it with some nitrogen producing starting material. If you want to prepare borates, you have to mix it with boron, elemental boron or diboron, or if you want to prepare carbides, then you have to mix it with reactive carbon powder. So, when you try to use a metal and a non-oxidizer as fuel, you make a mixture of it and then you spark it, then you can actually initiate a very high temperature reaction, and thereby you can get all these high temperature ceramics. These are, otherwise it is impossible for you to prepare in a lab scale, or we need to use a conventional furnace which is operated at 2200 degrees C, which can be used for making borates or carbides. So, this is a very versatile process, and in the next slide I will show you a small clip of a movie which shows how this high temperature material works. And Professor Merzanov is actually the academician of the Russian Academy of Science, and he has authored many journals based on SHS technology. In fact, this process is so very popular that there is a separate journal called International Journal for Self Propagating High Temperature Synthesis, and it has been there in the shelf for more than 20 years, and still many novel approaches are being made using this technology. This technology also has been used to make ferrite magnets useful for industrial application. Pankhurst and co-workers, they have used this process to prepare this sort of ferrite material. What you do here is take all the starting materials together, like magnesium oxide, zinc oxide, iron, Fe2O3 and potassium perchlorate. Potassium perchlorate in this case acts as a oxidizer, and they form a mixture together, and the mixture is actually burnt. The reactions can be started by point source initiation, where a hot wire or filament is actually touching a pellet, and that will initiate a very high temperature reaction, and it can give you the final product, which is nothing but a ferrite magnet. Now the advantage here is, if you want, you can make it as a disc or a rod or a spiral ring, anything you can make, provided you make the shape of it in the precursor and then you try to ignite and start this SHS reaction. As you can see, these are very fast reactions, therefore in 4 seconds you can actually reach temperatures up to 1400 Kelvin. And you can see the span of this reaction is not lasting for more than a minute. It is always less than a minute, therefore it is a rapid self propagating one. So just initiate, that is enough, you do not need to run through or sustain the reaction by heating it. That is why it is called self propagating, because once you initiate, it can propagate on its own and it can complete the reaction. And you can see from this profile, by 27 seconds almost the combustion is over and it is cooling back. This is the IR image, infrared image of this zone, which clearly shows how the temperature propagation is occurring from a low temperature to high temperature, and against each time scale. 4 second, this is how the propagation is, 10 second, this is how the propagation is. So between 4 to 10 second, it almost hits the maximum temperature and then it starts cooling down. Now this is being conducted also in the absence of field and in the presence of field. For example, the same composition has been prepared in using an external magnetic field of say 3 Tesla. Okay, so I have included this point, SHS in large magnetic fields. So if you take the specimen at 3 Tesla and if you take the specimen at 12 Tesla, you see a much harder and much sintered magnet is formed at a higher temperature. The passage of why? Because the passage of the wave induces an electrical pulse and a small magnetic field, both of which are thought to be caused by the movements of ions and electrons at the molten reactant front, and because it generates a electrical pulse and a magnetic field, then the external magnetic field can also propagate a wave which can initiate in the soldering or in the sintering process of this final product. So if you are actually looking for making a fine finishing of the preferred form or shape of your ferrite, then application of external magnetic field also influences making such materials. So this has been widely exploited as SHS, but the word combustion has not been used till then, rather it has always been referred to as self propagating high temperature synthesis. This is a movie that I want to show just to give you an idea what this self propagation is and how much of energy is involved and how we can initiate such a reaction, if you can carefully look at the animation. So this clip will help us realize how the combustion can be initiated and what sort of temperatures can be achieved in short time scale, and let us look at this movie. So what we need is a heat oxidizer and a fuel to initiate such a reaction. So the metal complexes we can form are of this nature, and this is made into a pellet like this. Yeah, in such a short span, in less than 2 minutes or so, it is possible for us to realize a product, as you had seen in the last phase, a small pellet can actually give you almost a 10 centimeter long metal foam, and this is one of the way this high temperature reaction can be achieved. But also it might look scary because it is actually kept in a confined medium where it argon is surfaced through this reaction, because you do not want oxide. In case of metal foams you have to supply argon atmosphere, but can we make this bit more easier is the question, is a open challenge, and can we extend this sort of high temperature reaction for many of the other materials other than merely metals and alloys. That is the question that we need to understand. So, the point that we need to note is combustion reactions can become explosive in nature if the O by F ratio, that is the oxidizer to fuel combination, is not controlled, and if the reaction is not done in an open vessel, this can become a potential explosive situation. Therefore, we need to be careful to control this reaction by doing such experiments in a open vessel. Now, how to tame combustion synthesis to make material is what we are going to see. One of the option is to use a solution process, because as you have seen in the earlier cases, it has always been a dry mixture of all the ingredients mixed with the powerful oxidizer, and when you spark it you get the corresponding oxide or metal. But the other possibility is to use a solution process, and what is the objective of using a solution combustion reaction? Number one, we can use different metal salts, because we do not need to necessarily always start with pure metallic powders, which is often very costly. But if you go for metal salts, those are cheaper, available easier, and you can use it in larger amounts for scale up activities. Therefore, this is one of the prime motive why we can resort to a solution process. Number two, when we try to make a quaternary mixture of metals in the final product, then you can actually govern or you can hold the stoichiometry together, because you can carefully start with stoichiometric amounts of corresponding metal salts. Also, this can be a rapid one step synthesis, because you do not need to necessarily mix all these solids to bring it into intimate contact, because in solution when you bring everything together, then they are stoichiometrically and intimately mixed, and as a result the metal ions can be brought to atomic level distances. So, once metal ions in atomic distance and then you initiate a combustion, then the final product actually will be a purely stoichiometric compound, which is desired for us. So, for this reason one can resort to a solution process, which is a viable alternative to the known SHS technology. So, the person that I would like to highlight and bring to notice is Professor Patil's group at IISc, who pioneered this field called solution combustion synthesis, and it was such a fascinating discovery of making oxide materials that this was the first ever review that was written on the solution combustion synthesis by Professor Patil in Bulletin of Material Science in December 1993. For those of you who are interested in knowing the history of how this solution process was developed, one should read this article. Therefore, I have quoted this particularly, and I also would like to record the other pioneers in this field, including myself. This is Dr. Kingsley, who was the first person to publish a PhD thesis on this combustion synthesis, and this is an interesting photograph which we took in late 86, where you can see Kingsley holding a petri dish, a glass dish containing alumina powder. I will show this photograph in the next slide, and this was the first ever result that came out from solution combustion synthesis, which was developed at IISc Bangalore. Now the solution combustion synthesis, when developed, it can actually result in foamy residue of metal oxide particles. For example, you can see this is a petri dish which is of 300 ml capacity, and in this 300 ml capacity dish, you can actually fill the whole dish with powder which will just weigh only 2.72 grams, and this can be such a fine and porous powder that you can prepare, which has very high surface area with very low particle size. There is no other method by which one can prepare a compound like alpha alumina, which is a high temperature form, because when we try to make alpha alumina, it is usually a high temperature oxide. Therefore, you have to heat it to very high temperature in a electroheating furnace, and in such case you will always end up getting a sintered product which will be 1/100th of the volume that it will occupy. So it is a very important reaction which gives high temperature phases with lot of special surface features. The first paper that was published on this solution combustion synthesis was published in Materials Letters, which is the pioneering publication made by Kingsley and Patil, and as you can see here, a list of aluminum based compounds were prepared, including magnesium aluminate, calcium aluminate, yttrium, aluminum garnet, zirconia, lanthanum aluminate, and including ruby powder have been achieved. The main feature of that is you can prepare all these compounds by just maintaining a solution at 500 degrees C, which will get combusted to give this high temperature ceramics. We will look at some of the issues in greater detail in the next few slides. The range of compounds what was published in the first paper include alumina, and as you know, YAG is a laser material, and then tetragonal zirconia is a toughened ceramics, and then this is a electrolyte beta alumina, and then LaLO3 is a very good precursor material for thin films. So you could see here vividly that almost all the aluminum based compounds were prepared in the first instance using this combustion procedure. So what is this combustion? Combustion of a proper combination of an oxidizer and a fuel. This can produce the exothermicity required for simultaneous synthesis of oxide ceramic powders. So when a combustion is generated because of a proper combination of an oxidizer and fuel, the energy that is released is actually used by a simultaneous formation of the metal powders or metal oxide powders, and for this reason oxidizers which include metal nitrates and the fuels can be urea, carbohydrazide, glycine and others have been used successfully as fuels. I will come to this list in greater detail. The metal nitrates are good oxidizers, therefore you can either take a divalent metal or a trivalent metal nitrate. Those which are divalent are magnesium, manganese, iron, cobalt, nickel, copper, zinc, strontium, calcium, barium. All these have the ability to form nitrates, and they are bivalent, and trivalent ones are all the lanthanides, lanthanide ions as well as aluminum. So if you are looking for, in fact chromium also can be included because chromium nitrate is also trivalent. So if you want to prepare chromates, then you have to start with chromium nitrate. If you want to prepare aluminates, then you have to use aluminum nitrate. Metal perchlorates, as a word of caution I want to register here that metal perchlorates, although they are oxidizers, they are very hazardous, because they can produce lot of oxygen or oxidizing atmosphere they can produce, but what happens is when you try to do a combustion, the perchlorates can actually transform into metal acids in combination with the fuel, and therefore they can behave as explosives even on a lab scale. Therefore caution has to be taken that there should be no reference to making metal perchlorates as oxidizers when you do combustion for making material synthesis. Organic fuels, particularly those containing nitrogen, also serve as a complexant in the precursor which inhibits inhomogeneous precipitation. Therefore any fuel that you are taking, if they are rich in nitrogen, they will invariably prevent complexation. As a result, when you add a fuel to a metal nitrate solution, there will not be precipitation, rather it will form a clear liquid. Therefore the organic fuels that are preferred are those which have more number of nitrogen, and they also participate in a effective combustion reaction. So such organic fuels are needed. The predominant ones are hydrosides, but do we really need hydrosides? As I told you in the initial part of my lecture that hydrosides, monomethyl, dimethyl hydrazine, these are used as propellants, but we do not really need to resort to hydrazine. What we can do is we can even start with a simplest of such molecules, organic fuels, as simple as urea. Urea, as we know, is not considered to be a fuel, it is considered to be a good fertilizer otherwise, but from the propellant chemistry principle we can observe that even urea can play a role. Why? Because on oxidative decomposition urea will actually go out as either as ammonia and carbon dioxide, or they will go as nitrogen and hydrogen and carbon dioxide upon complete combustion. So urea is a very good fuel, plus it does not leave any residue as impurity. The simplest other one other than urea is glycine. I will show some examples of how this should be actually CH2. This is glycine, and then you have carbohydrazide, and then you have malic dihydrazide. All these sort of hydrazines are simple ammonia based organic molecules, can be used for the combustion as fuels. Combustion methods are particularly well suited to producing multi-component metal oxides yielding compositionally homogeneous fine particles with low impurity content. This is the speciality of this wet chemical route. The exothermic redox decomposition of these oxidizer fuel mixtures is actually initiated at low temperatures, usually less than 250 degrees C. As you would see from another animation that it is very easy for us to prepare such high temperature materials using a wet chemical combustion procedure, where you just initiate the reaction with as low as 250 to 500 degrees C. Now in a regular protocol for a solution combustion synthesis it is very easy, because in step 1 all that you need to do is take a proper combination of a fuel and oxidizer and make a homogeneous solution in a beaker such as this. This is a glass beaker, and you have to take very minimum amount of water and not excess amount, because when the reaction is occurring sometimes the fuel can be destroyed when it goes through a long heating time. Therefore we need to have a minimum amount of water just to dissolve both the oxidizer and fuel, and once you insert it into a furnace then you see a typical combustion reaction such as this happening, and after the combustion reaction the solution is actually converted to a product. And this is a example of preparing ceria doped with platinum, example I will quote in the slides to follow. So what is the time scale? From the time you make the solution and you get this product, after inserting it through a furnace, the whole thing takes less than 2 minutes. So in 2 minutes time you can achieve such a high temperature reaction. This is a movie which I want to show before I touch upon the issues related to combustion synthesis. So I just want you to watch this movie. What you see here is a muffled furnace, a open muffled furnace, and this furnace is actually maintained at 500 degrees C. So, what you can do, instead of taking a petri dish, you can even use a 250 or 500 ml beaker and take the solution and put it inside a preheated furnace, and then you would see the sort of reaction that is happening. So, as you see, you have the oxidizer and the fuel which is going through complete dehydration, and the excess water is actually coming out as you are heating it. The first few seconds you can see some sort of a frothing that is happening, and after that this combustion reaction occurs. During the combustion you can actually see how the wave propagation is. The exothermicity is actually propagating from the top downwards, and as and when the reaction is the temperature is used for converting that solution mixture into oxide, then the oxide is coming out, and then the propagation is actually going down. And once this is done, you can see that the ruby powder that is formed is coming out, and you can see the pinkish tinge in this solid product. And if you take the PL for this ruby powder, you can see the excitation spectra and the emission spectra exactly matches with that of a ruby crystal. And as you know, ruby crystal is nothing but a laser material which is used for making ruby lasers, and they show a characteristic emission around 695 nanometer. So, if you get such a sharp emission peak, then you can be sure that it is actually a lasing action that is coming from ruby powder, and this ruby powder incidentally can be prepared from mixing less than 1% of chromium nitrate in aluminum nitrate. So, whatever that is coming out is not alumina powder, but it is actually ruby powder, that is chromium atomically doped in the aluminum sites of aluminum oxide. So, this is a fabulous reaction where such low level impurities can be very nicely incorporated into alumina matrix. This is not the only compound. We can make n number of compounds out of such approach. All you need to do is, depending on the end stoichiometry, we need to take the corresponding metal nitrates to prepare such oxides. Properties of these products are therefore influenced. They are influenced by the nature of the fuel and the oxidizer fuel ratio. Many technologically important oxide ceramics can be produced by this method. So, I will try to take you through few examples to show you how the fuel content is important, and what is the relevance of this oxidizer fuel ratio, and how do you calculate this oxidizer fuel ratio to make such combinations. The key principle in combustion reaction is the efficiency, and this efficiency of combustion is actually calculated by the oxidizer to fuel ratio, which is given as QE or phi E, we can call it, is nothing but a summation of the coefficient of oxidizing elements in the specific formula into valency over minus 1 into a sum of coefficient of reducing elements in the specific formula into valency. Therefore, if you have your metal nitrates, you can actually calculate the oxidizing valency in the numerator, and if you have a fuel, then you can calculate the reducing valency of your organic fuels based on their valency. So, accordingly, a stoichiometric proportion of this reactants should yield Q by E should be equal to 1. If Q by E is equal to 1, then you can say then the combustion efficiency will be at its maximum. But there is a case when if the fuel the efficiency is less than 1, that means it is a fuel lean composition, meaning there is more oxidizer, though, so you need to lower down on the oxidizer proportion, and there is a fuel rich case when the phi E is less than 1. So, both this has to be avoided, and preferably it is always better to take a fully stoichiometric situation. But then when you are actually taking metals in the initial phase during the combustion can get reduced to metallic metal, which can also catalyze the combustion, therefore the exothermicity can be more. In such cases always it is better to play down with a fuel lean mixtures than fuel rich mixtures. So, depending on the type of reaction that you are aiming, you need to fine tune on the oxidizer to fuel ratio. For example, let us take the case of barium hexaferrite, which is one of the compound, and the barium hexaferrite has a composition BaMg2 Al16O27, and this barium hexaferrite can be prepared using urea. And if you want to balance this equation for a complete combustion, this is how it looks like, where you take 45 moles of this barium nitrate, magnesium nitrate, aluminum nitrate to give barium magnesium aluminate, sorry, this should be barium hexaaluminate, I am sorry about it, this is barium hexaaluminate. But what you should understand is during complete combustion you will have 90 moles of water which is released, and this water will actually go as the initial step in the decomposition process before the combustion occurs. But when the combustion occurs, you actually have 45 moles theoretically possible, 45 moles of carbon dioxide and 72 moles of nitrogen that is released upon complete combustion. And this is one of the important features of the solution combustion process, because it is a gas releasing exercise. Enormous amount of gases are released. As a result, the final residue will always be a porous and a finely divided metal oxide. If this much amount of gas is not released, then it will be a highly sintered compact. So, if you want to prepare nano dimension stuff, then you should actually favor a solution combustion process, because of the gas evolution it gives a highly reactive solid. And as you saw from the movie, the whole process is actually occurring in less than 1 minute time, and the gases which are trapped is the ones which are hypergolic, which is giving this high temperature, and because of these gases which are released during the combustion, they are not sintering the particles. Another thing, the whole reaction is also run in a beaker, in a glass beaker. It is a phenomenal reaction, because even though such high temperatures above 1000 degrees are achieved, yet we are not seeing the glass melting. And this glass is not melting even at very high temperatures, because the energy that is released during the combustion is actually dissipated or flushed out by the escaping gases, number 1, and the reaction mixture is also consuming this energy to transform into the corresponding oxide product. As a result, even though you are using a glass vessel with very high temperature, the glass does not melt at all, because it is a fast quenching technique. So, one of the things that we need to understand is that when we try to take a mixture of metal nitrate and fuel, in this case the calculated ratio as far as the oxidizer fuel ratio is concerned has to be 2.36. So, when you control this fuel to oxidizer ratio, then it will be possible for us to control the exothermicity of the reaction. Now, we can also play around with different compositions or different combinations. For example, the fuel to oxidizer ratio can vary with the sort of the reducing valencies of the fuel, and in this case urea, if you take urea, then for the energy to be maximum, this is the dictated formula, fuel to oxidizer ratio. But if you can also play around with this 3 or with 1, which is a fuel lean situation. In such cases you will see the efficiency will vary and it will not be equal to 1. Now if you go for carbohydroside, you see for the fuel efficiency to be 1, in this case the fuel to oxidation ratio has to be 1.78, whereas in this case for urea it was 2.36. That is because the number of reducing valencies in carbohydroside is different from the number of reducing valencies in urea. I will give you one more example of how this fuel ratios can influence. For example, you take the barium hexaaluminate which is doped with urea. If you take the fuel to oxidizer ratio at 3, or if you take fuel to oxidizer ratio at 2.36, you can see the change in the crystallinity. This is according to the O/F ratio, but this is not according to the O/F ratio. As a result, you can clearly see the crystallinity of the end product is varying. So this is proving very crucial, and again in this example you can find out that if you vary the fuel to oxidizer ratio depending on whether it is a fuel rich or fuel lean or stoichiometric, you can see that there is an enormous change in the crystallinity for the same composition. So the oxidizer to fuel ratio is very critical in this example, and once you make that, you can clearly see that the commercially available barium hexaaluminate is almost similar to the features of combustion derived powders. So we can make commercially viable synthesis if we can scale it up to proper proportion. We can also see in this profile the relative intensities of this barium hexaaluminate doped with europium. You can see the depending on the oxidizer to fuel ratio, either using urea or carbohydroside, the PL is drastically changing for this phosphor. So we have to optimize which is the proper stoichiometry for getting the right type of property that we desire. This is another example of what are all the important phosphors that can be prepared using the combustion synthesis. As you know, yttrium silicate doped with ceria can be used for scintillators application. We have strontium aluminate doped with europium for long lasting phosphorescence material, strontium aluminate with dysprosium, terbium. Then we have europium activated LaLO3 as red phosphorus. We also have yttria doped with europium as red phosphor in CRT tubes, so on. So a host of phosphors can be prepared using this combustion synthesis. Here is another example of how with the doping concentration of terbium in yttrium aluminum garnet, one can change the luminescence of the resulting powder using combustion synthesis, and these are all the YAG powders which are activated at 254 nanometer excitation. Now I will give one example of how crucial the oxidizer can play the role. Effect of oxidizer on the combustion characteristics. This is a paper which appeared in 2010. I just picked out this paper because even now people are experimenting on making nano sized iron oxides. This has appeared in International Journal of Self Propagating High Temperature Synthesis. Although it is nearly 24 years since this process was devised, still lot of activity is going on. I am just going to point out to you the use of ferric nitrate and ferric oxalate. Ferric oxalate is used as a oxidizer in one hand, and ferric nitrate is also used as a oxidizer, where glycine has been used as the fuel. In both cases glycine is used, but because we do not have nitrate here, extra nitrate is used in the form of ammonium nitrate. Suppose I do not have a metal nitrate, then we do not have to worry about it. You can take a salt of that particular metal, and you can compensate for the combustion reaction to occur by taking ammonium nitrate separately, that is also possible. So, if I take this combination or if I take this combination, you can see how the property varies. As you see here, this is the TGDTA for both these combinations. If you take iron oxalate, ammonium nitrate and glycine together, the exothermic decomposition is occurring somewhere around 182 degrees C, whereas if you take metal nitrate, iron nitrate with glycine, you can see phenomenally the combustion reaction occurs at a very early stages. There is a difference of around 40 degrees if you take metal nitrate compared to iron oxalate. So, the starting material can actually play a important role in the combustion. Not only that, the resulting powders also determine the quality of sample that you can see. If you take iron nitrate as starting material with glycine, look at the porosity here, 100 micron or 40 micron, the enlarged version, you can see so much of porosity on the metallic oxide foams that are produced, and this porosity will determine the surface area also. Whereas if you take iron oxalate and ammonium nitrate separately, then you can see that hardly there is any porosity and it is all well sintered. Therefore, this iron oxide what you get here will be more sintered and less surface area material compared to the other one. And you can also see the morphology of the iron oxide powders starting with the oxalate and nitrate. So, distinctly it alters the surface properties. Now, the effect of combustion synthesis on the metal oxide composites, I will now show you some example of the systems. So far we have seen the effect of fuel and oxidizer. Now, I will tell you what all we can achieve out of such combustion reaction. We do not have to exactly make metals alone or oxides alone, we can also make composite materials. This example I have already shown you. The reaction is nothing but doping platinum in ceria or cerium oxide, titanium oxide composites. Why they are used? Because these are very powerful auto exhaust catalysts. Ceria impregnated with platinum or ceria platinum doped with the TiO2 is used as a automobile exhaust catalyst. But what you see here, after some cycle this catalytic converters are dead, they are poisoned because of the outcoming exhaust. As a result, the efficiency goes down. But if you use combustion reaction, you can see the activity is enhanced to a greater order. The mechanistic pathway for such reaction is given here, where your carbon dioxide is coming, getting absorbed with the molecular oxygen, and you can see there is a competing interaction on the surface, and then the carbon monoxide goes as carbon dioxide and it cleaves out, and this is the mechanistic pathway. But what makes this combustion process interesting is that unlike the other cases where you try to prepare alumina with platinum or platinum with ceria or platinum with the titania, they are all surface adsorbed. So, the noble metals will actually do the catalytic process with the host material almost as a mute spectator. But in the combustion process you can see that the platinum, cerium, palladium, everything is actually doped. They are not as zero valent metals, but they are here as ions. Once they are substituted effectively into this host lattice, then the conversion process of carbon monoxide to carbon dioxide is 15 to 20 times faster than the conventional reactions. As you can see here, this is a profile of carbon dioxide formation as a function of temperature. If you just take ceria without doping, then this is the conversion profile, but once you dope just with the 2% of palladium, you can see the shift in the in the temperature range, and the way it is so highly selective, the conversion is very selective and it is much faster, mainly because palladium is not actually sitting on the ceria, but it is actually doped into the lattice, and palladium actually goes to palladium 2 plus and cerium 4 plus goes to cerium 3 plus, and therefore it is now more as a substituted catalyst rather than a composite. As a result, you see a remarkable conversion of CO to CO2, and this can easily replace all the noble metal catalysts in today's automotive industry. Similarly, you can also see just 1% of palladium that is doped into TiO2 can actually push the conversion even to near to room temperature. So, if you use this 1% palladium doped TiO2, you can see the conversion as low as 50 degrees C. At 50 you can convert all the carbon monoxide to carbon dioxide. Why this is useful? Because the combustion route has a peculiar way of pushing the noble metal into the lattice, and because they are sitting inside the lattice, the way the conversion of CO to CO2 goes is very facile. We can also try to impregnate this catalyst onto this sort of cordierite monoliths. This is typically the way the exhaust catalysts are embedded in the converters. You can uniformly coat it and make it a useful catalyst bed. We can go for several such catalysts to get this done, and similarly we can make composites of ZrO2 and CuO2 ZrO2. Several such composites can be made, of which alumina, ceria, yttria, zirconia. You can see all these powders which are known to show surface area less than 1 meter square per gram can show such a very high porosity and high surface area. Now just 2-3 slides I will try to wind up to show that there are other ways to initiate this combustion other than merely using a furnace. So I call this as furnaceless combustion synthesis, which is actually microwave ignited. If you do not have a furnace, you can use a simple kitchen microwave to initiate this process. Advantage is you are generating the heat from within the solution mixture rather than heating from outside, and you can clearly see that in this the mass also plays a role. Instead of using a conventional synthesis, you can use a microwave synthesis, and in 2 gram quantity this is the way the crystalline magnesium aluminate is formed, but when you use 100 gram quantity you can get a crystalline form. This is one reaction, and I can show you another example. This is another thing that is happening which is of interest, where combustion reactions are experimented in microgravity. Therefore, for space applications you need to study at 0 gravity how this combustion proceeds, and NASA is particularly taking this as a active program to consider how combustion synthesis can occur at 0 gravity or microgravity, and this combustion reaction can also be used for making a reel to reel impregnation of this nanopowders into several layers, coatings. So this is not only done in a lab scale, but this can be done also in a industrial level. Lastly, I just want to conclude that this combustion process has gone into many spheres. Now it is being referred with many names. It is called popularly wet combustion route. Some people call this as materials born out of fire, and this is also referred to as furnaceless combustion and instant combustion synthesis. So there is lot of potential for many more interesting physical and chemical properties to be studied using this simple combustion technique.